The elimination method. The elimination method is useful for solving small linear systems. In particular, it works really well for solving systems of two equations in two variables. Let's look at an example. X plus y equals 2, x minus y equals 2. We can solve this linear system pretty quickly by simply adding the two equations, because when we add them, the y's go away, and we get 2x equals 4. Notice that x plus x is 2x, and positive y plus negative y is equal to 0. And we also have 2 plus 2 equal to 4. We now have an equation just involving the variable x, and we can solve this easily by dividing each side of the equation by 2 to get x equals 2. We still need to figure out what y is, and we can do that by substituting 2 for x back into either of the original equations. Let's just go ahead and plug it back into the first equation. We get 2 plus y equal to 2, so that y is 2 minus 2, which is 0. It follows that 2, 0 is the only solution to this linear system. Let's just check that the point 2, 0 actually satisfies this system. For the first equation, when we replace x by 2 and y by 0, we get 2 plus 0 equals 2, which is true. For the second equation, we get 2 minus 0 equals 2, which is also true. Let's also go ahead and sketch the graphs of these two linear equations to see that the point of intersection of the two lines will be the point 2, 0. The first equation, x plus y equals 2, looks like this. Notice that I plotted the two intercepts. We get the y-intercept 0, 2 by replacing x by 0, and we get the x-intercept 2, 0 by replacing y by 0. And once we have those 2 points, we could just draw a straight line through them to get a nice quick graph of that first equation. Similarly, the second equation has intercepts 0, negative 2, and 2, 0. And we see that the point of intersection of these two lines is the point 2, 0, as we found before algebraically. Let's look at another example. X minus 3y equals negative 3, 2x plus y equals 8. In this case, it's not as simple as just adding the two equations, because if we were to add these two equations, neither of the variables would go away. Another thing that we're allowed to do that won't change the solution set of the system is we can multiply either equation by any non-zero number that we like. Multiplying the first equation by negative 2, for example, will do the trick, because then we get negative 2x plus 6y equals 6. And when we add this to the second equation, 2x plus y equals 8, the x's will go away, right? Because negative 2x plus 2x is 0. We also have 6y plus y equal to 7y, and 6 plus 8 equal to 14. We now have an equation just with the variable y, and we can solve this by dividing each side of the equation by 7 to get y equals 2. Once again, we should replace y by 2 in either of the two original equations and then solve for x. Let's go ahead and plug y equal 2 into the second equation. We get 2x plus 2 equals 8. Subtracting 2 from each side gives 2x equals 8 minus 2, which is 6. And dividing by 2 gives us that x is equal to 3. So it follows that 3, 2 is the only solution to this linear system. Okay, another example. 3x plus 5y equals 0. 2x plus 3y equal to 1. So there are many things we can multiply by here to get one of the variables to match up. We could use fractions and just multiply one equation by a single number, but to avoid messy fractions, I'm going to instead multiply each equation by a non-zero number. For example, I can multiply the first equation by 2 and the second equation by -3 to make the x's match up as negatives of each other, so that when we add the two equations, the x's will go away. Take a look at this for just a second and see if you understand why I chose these two numbers. Okay, so when we multiply the first equation by 2, we get 6x plus 10y equal to 0. And when we multiply the second equation by -3, we get -6x minus 9y equal to -3. Now notice when we add the two equations, the x's go away. 10y minus 9y is y, and 0 minus 3 is -3. I'm now going to go ahead and substitute y equals -3 into the first equation, 3x plus 5y equal to 0. And we get 3x plus 5 times -3 is 0. 5 times -3 is -15. Adding 15 to each side of this equation gives us 3x equal to 15. And dividing each side of this last equation by 3 gives us x equal to 5. So we see that 5, -3 is the only solution to this linear system. Another example. 3x plus 9y equals 6, 4x plus 12y equals 9. What would you multiply each of these equations by to eliminate one of the variables? How about we multiply the first equation by 4 and the second equation by -3? So we get 12x plus 36y equals 24, and -12x minus 36y equals -27. Notice when we add the two equations, both the x's and y's cancel in this case, and we get 0 on the left, and on the right, 24 minus 27 is -3. This is a contradiction. I use that little lightning bolt symbol there to indicate we have a contradiction. Something went wrong. And what went wrong is that there are no solutions to this linear system. This linear system is inconsistent. Unlike the previous linear systems that we looked at, which were all consistent linear systems because they all had solutions. One more example. -2x plus 8y equal to 4, 3x minus 12y equals -6. What are we going to multiply by? Okay, one option is to multiply the first equation by 3 and the second by 2. We then get -6x plus 24y equal to 12, and 6x minus 24y equal to -12. This time when we add the two equations, everything cancels. -6x and 6x is 0, 24y and -24y is 0, and 12 and -12 is also 0. The equation 0 equals 0 tells us that the two equations have the same graph. So the linear system has the same solutions as the single equation -2x plus 8y equal to 4. The solution set of this single equation is the set of points of the form x, 1/2 plus 1/4 x, where x is a real number. To see where that expression comes from, let's solve this equation for y. We add 2x to each side of the equation to get 8y equals 4 plus 2x, and then divide through by 8 to get y equals 1/2 plus 1/4 x, so that the solutions to this linear system are all points of the form xy, where y is equal to 1/2 plus 1/4 x. This is an example of a consistent linear system with infinitely many solutions.